So, speaking of derivative rules, let's talk about derivative rules. So at the top of the page here, we summarize some things. Here's the definition of derivative. If the derivative exists, we say the function is differentiable. Here's something new. Here's some different notations. So if you've got like a y equals f of x, there's the f prime of x. That's the notation we've been using for derivative. But there's a couple other notations. I like to use this notation, dx f of x. So the d stands for derivative. The x means that that's the variable of differentiation. So I'm taking the derivative of f of x with respect to x. That's what that means. I like this notation. I use it a lot because it shows you the derivative as an operator, as a process. All right. And so when we go through, as you see today, these steps, I think this is a cleaner way to do it. All right. Once again, the book doesn't do it this way, but I like to do it that way. Remember that the derivative itself is the ratio of slopes, right? The numerator here is the change in y. The denominator is the change in what? X. So it's really the limit as delta x goes to 0 of delta y over delta x. And so that explains this next notation. It's called the Leibniz notation. Dy dx is another way they can ask for the derivative. The delta is the discrete change if you have two different y's and two different x's. The dy dx is that instantaneous rate of change. You're looking at the slope at a point as opposed to the slope between 2 points. And so another way you can write the derivative as an operator is you could write d dx f of x. And then if you take physics classes, sometimes they'll denote derivative y with a single dot over it. So these are all expressions for derivative. In this course, we'll stick to these here. So we have properties of derivative. So these are theorems that you can prove using the definition of derivative, and I've uploaded some videos where we actually go through the proof of them. Bless you. But we can hopefully make sense of some of these. The constant rule. What's the derivative of a constant? Well, if we think about this as a rate of change, if something is constant, is it changing? So its rate of change is what? 0. We can think of this graphically, because if you graph a constant function, what's the slope of a constant function? 0. So the derivative of constants are 0. Does that make sense or not? The pollen count's through the roof today, by the way. So everyone, I mean, it's insane. I woke up at 2 in the morning, couldn't breathe. So I just sat up with my dog. The power rule. Well, let's talk about this. What if you're looking at the derivative of like a linear function, mx plus b? Linear functions have a constant slope. What's the slope at any point on that line? M. So that's going to be m. But more specifically, the derivative with respect of x with respect to x is what? It's 1. Okay. More generally, if you take the derivative of x to a power, it's that power times x to the power minus 1. And this is not very obvious. Although yesterday we saw this, we went through the limit process and saw this. Throughout the semester, I'll have videos uploaded where we prove this rule for more and more exotic powers. To prove it for natural numbers like x squared, x cubed, things like that, you just have to pull out the binomial theorem from pre-calculus. But people don't remember that. You remember Pascal's triangle? No. So it's on the video. And then when you go into fractional powers and things like that, you can use the stuff we learn later on. So throughout the semester, if you're interested, we have all the proofs there for you. But it even works for stuff like square root. And you're like, well, wait a minute. How does it work for square root? Remember, square root is what power? 1/2 power. So this does work for square root. The power comes down front and then gets demoted by 1. So this would be 1/2 x to the minus 1/2. Okay? So the power rule does work for any power you want. But there's a price to pay for this, and that's all in the proof. And then we have a couple of rules governing arithmetic. We've got the constant multiple rule. So if you're multiplying a function by a constant, you can bring the constant out front. Remember that at the end of the day, functions are limits, or excuse me, derivatives are limits. So if you think about this limit definition here, if you multiplied your function by a constant k, then you could factor that constant k out of the numerator. Can you factor constants out of limits? Yeah. So that's why that works. Or if you think about it in terms of rate of change, if you know the rate of change of something, and then you multiply that by a factor. So if I think about this graphically, so if here's like a y equals x, or f of x rather, versus a y equals 5f of x, and I think about the ratio of delta y over delta x, the y values here go up 5 times as much as the y values here. You follow? So if I look at the rate of change of y over x, the rate of change of the 5f of x is going to be 5 times as much as the rate of change of the regular f of x. Does that make sense or not? Sum and difference rule. The derivative respects sum and differences. So you can either add or subtract, then take the derivative, or take the derivative and then add or subtract. Okay? Once again, think about it in terms of limits. If you had a second function in here, plus or minus, can you split the fractions up over plus and minus? Can you split limits up over plus and minus? So therefore you can split derivatives up plus or minus. If you think of things like rate of change, let's say you're on a train. Let's say the train is going, I don't know, 40 miles per hour. If you're walking in the train at 5 miles per hour, then to an observer, you're really going how fast? What do you do with those rates of change? You add them. You'd be 45. You follow? If you're going this way, then you'd be going how much? 35. And that's the principle of relativity for you. You can use this kind of argument to prove that there is no such thing as simultaneity. If you think, oh, these things happen at the same time, there is no such thing as the same time. You can always find a reference frame where things are later or different. It's pretty wild. All right. So let's look at some of these properties. Now, if you've had the calculus before, good for you, right? But if you haven't had it before, I'm going to go through every single step and explain the process because we have some properties. The question is, how do we apply those properties? And the rule of thumb I use is the first derivative property we use would be the last operation we would do to evaluate the expression. So it's kind of like an onion. We kind of work from the outside in when we apply these derivative properties. So let's take a look at our first one here. F of x is 3x squared minus 6x plus 2. And they're asking for f prime of x. And we know that f prime of x means they're asking for the derivative. So here we go. There's my derivative. And I think you'll see as we work through these things why I prefer this notation for derivative, because it's going to show us what's actually happening in each step. So if you imagine plugging a value in for x and simplifying everything, you'd square it, you'd multiply it by 6, you'd multiply it by 3, then you take 3x squared minus 6x plus 2. So the last operations you're doing in that computation are the what? The addition and subtraction. So that means that's the first derivative rule we're going to apply. Here's the sum and difference property. So I'm going to take the derivative of the first term minus the derivative of the second term plus the derivative of the third term. Now I look at the first term. If I plugged an x into the first term, I would square it, then I'd multiply by 3. That means the first derivative property I'm going to apply to that first term is to multiply by 3. 3 is a what? Constant multiple, so what can I do with it? Bring it out front. In the second term, I would plug x in, I'd multiply it by 6. The 6 is a constant multiple, so what can I do with it? Bring it out front. And now I've got the derivative of 2, which is what? That's a constant. The derivative of a constant is 0. Now I got the derivative of a power x squared. What's the derivative of a power? The power comes down front and gets demoted. We take 1 away from it. What's the derivative of x with respect to x? And so finally, grand final answer, I get 3 times 2, which is 6, x to the first power, which is x minus 6 times 1, and that's my derivative. Okay? So if you went through the limit process that we talked about yesterday and did all the algebra, you would end up with 6x minus 6. Any questions on how we parsed this and broke it up? Remember, in mathematics, yeah, question?
Oh, yeah. So you said like the last step would be like addition and subtraction, so that's the first one you start with. Right?
Yep. Mm-hmm.
Okay.
So always imagine plugging stuff in, and the last thing you do is the first derivative. So remember, I talked about this. I'm going to point this out here. Remember, the big ideas here are analysis and synthesis. Analysis means breaking things down into the small parts. Synthesis is putting them back together again. So just like when we had, remember those limit properties? We had the basic limits, and then we looked at these functions, and the limit laws helped us put those basic things together. Do you see how the same thing's happening here? I know the derivative of constants, and I know the derivative of powers of x. So what did we do with this expression? We took this complicated expression and we broke it down into those constituent bits, took the derivatives of those bits, and then put the derivative back together using those derivative properties. Okay? That's a big theme. I mean, that's what chemistry is all about, right? That's why you have your atoms and molecules, right? Find y prime if y equals 2 over x minus root x. So you see y prime, that's just another way for them to ask for the what? Derivative. So the first thing you might say is, wait a minute, Stitzy, we don't have a rule for division yet. We will in about 15 minutes. But even when we get the rule for division, you're not going to want to use it on this one. Because you can rewrite 2 over x as a power, can't you? Because what's the power on x down there in that denominator? It's really 2 over x to the what? First, which means I can bring that up to the numerator as 2x to the what? Negative 1. You follow? So I can rewrite this as a power. And likewise, the square root of x, as we mentioned a little bit ago, I can rewrite that as a power. That's x to the what? 1/2. So before I do any calculus, I'm going to do some algebra. There it is. Now imagine plugging an x into this expression. You would figure out x to the minus first, multiply it by 2. Then you'd figure out x to the 1/2. And the last thing you would do is subtract those two quantities, which means the first derivative rule to apply is the subtraction rule. So I would take the derivative of the first term minus the derivative of the second term. Now looking at the first term, if I plugged an x in, I take it to the minus 1 power, and then I would multiply it by 2. 2 is a constant that's being multiplied, so what can I do with that 2? Bring it out front. Here I'm all ready to go, because I'm taking the derivative of x to a power. What do? I bring the power down front, and it gets demoted. Subtract 1 from the power. And we're going to go to a new slide, but before we do so, any questions on what's on this slide? Y equals 2. Now, I've got an x to a power. So how does this work? The power comes down front and gets demoted. So it's minus 1, minus 1. Be careful there with the negatives. Minus 1/2 x to the minus 1/2. So for my final answer, I've got 2 times negative 1, which is x to the minus 1/2 x to the negative 1/2. Okay. Now at this stage in the game, leave the negative exponents. In short order, we're going to be having to rewrite those as fractions and get common denominators. But here's the thing about the back of the book. And some of you, I think, have already encountered this. I think Emily encountered this yesterday. Emily did the problem beautifully. Emily's answer did not match the answer in the back of the book, because the back of the book was doing some weird algebra, but we checked it on Desmos. You follow? So if you get an answer that doesn't look like the back of the book, check it graphically on Desmos. And remember, Desmos is whitelisted on the browser, so you can check on the test. You can have confidence that you've got the right answer. Okay? All right, let's take a look at this next one. Here they give us a y. They ask for dy dx. And remember, dy dx is just yet another way for them to ask for the derivative. Okay? Once again, before we don't have a rule for division, and once again, even when we get one, we're not going to want to use it on this one. We want to do some algebra first. So we've got to remember how fractions work. They call this in the book separating numerators. It's really just a distributive property. Okay? Really what's happening here is you're just taking a minus b times the reciprocal of c, and you're distributing. But some people like to think of it as separating the numerator. But that makes it sound like it's an operation you don't know what it is. But pretty much you can always break up numerators is what I'm saying. So if you have an addition or subtraction in the numerator, you can break it up. Be warned, however, this does not work for denominators. Okay, so it doesn't work, but it works in numerators because it's just distributive property. So what we can do is, once again, we only know derivatives for powers of x, and then we just know how things work over addition, subtraction, and bringing out constant multiples. So I have to rewrite this so it involves just addition and subtraction of powers of x and constant multiples. So we can rewrite this as a 6 over x, or 6x over 2x cubed minus 1 over 2x cubed. So once again, we're not doing any calculus yet. We're just doing algebra. Now, what's 6 over 2? That's going to be 3. And this is going to be x to what power? Up top, I've got an x to the first. I'm dividing it by x to the third. So this is going to give me an x to the what? Negative 2. Minus, what's the coefficient here? In the numerator, I've got a 1. Denominator, I've got a what? So this is really a 1/2. And then what's the power on x here? Negative 3. Are we all good with the algebra? Now, I have a sum or difference of powers of x with constant multiples, which means I can use the rules I know. What's the first rule I would use on this one? Sum and difference. So I'm going to go to the next slide. dy dx equals derivative of the first term, 3x to the minus 2, minus the derivative of the second term, 1/2 x to the minus 3. What rule can I use now in the first term? Constant multiple. Bring that 3 out front, times derivative of x to the minus 2, minus, what rule can I use here? Bring it out front. All right. How do we take the derivative of x to a power? What happens to the power? Comes down front, and then it gets demoted. Minus 1/2. Power comes down. What's 3 times negative 2? X to the, I got ahead of myself here, didn't I? It's minus 2 minus 1. This would be x to the minus 3. Now I got a minus 1/2 times the negative 3. That's going to give me a what? Plus 3/2 x to the negative 4th. Make sense or not, folks? Okay. All right, here's a video. So once again, I expect you to engage with these somehow. Maybe what you do is you try to get the derivative. If you get, and I put the answer there. If you get the answer, that's great. And then, but if you want to go in and look at explanations or something, then you got the video. Or you could fire up the video and take notes from the video. I don't care what you do, right? But these are some extra practice for you to do on your own. Okay, more rules. How does the derivative work with products and quotients? Okay, limits work just fine with products and quotients. As long as you're not trying to divide by 0, limits are all cool with that. But here we're looking at rates of change and slopes. Okay, so here's the product rule. I'm taking the derivative of the product f of x times g of x. Okay, so this is like I remember this because of how we used to go get haircuts as children. So I think I told you this before. Anyone can tell you, they can spot me a mile away that I'm a middle child. I had an older brother, younger brother. And what would happen is, the last day of school, we'd come flying home last day of school, and then you'd go to the neighbor behind us, who for some reason had a barber chair in his basement. Now back in the 70s, no one questioned that. People had stuff like that all the time. So we'd go over to Mr. Burkholder's house, go to the basement, and then we would all get our hair cut. But the rule was we all had to go together, and then each of us would get the haircut while the other two waited their turn. You follow? So this is what's happening. You got f and g, they're a product. Each of them is going to get their derivative taken while the other one waits. You follow? So you take the derivative of the first factor while the second one waits, and then you got the first times the derivative of the second factor. Okay? And if you think of it this way, it generalizes to however many factors you've got. Like if you were taking the derivative of f times g times h, you can use this same methodology. Say, okay, well, I got to take the derivative of the first one while the other two wait, plus I got to take the derivative of the second one while the other two wait. Plus I take the derivative of the third one while the other two wait. You follow? So, then you have as many factors as you want. And now I got the quotient rule, which looks like you would never, ever remember this. This is crazy. You got derivatives flying all over the place. It turns out, and if you've had calculus, you may know about this, there's a rhyme you can use to remember this. Right? There's a rhyme for this. And here's the rhyme. So let's take the derivative. What we do is we call the numerator, we call that the high function, because it's up high. And the denominator, we call the low function, because it's down low. And here's how the quotient rule works. You ready? It's low d high minus high d low. And then you square the bottom, and off you go. That's it. Low d high minus high d low, square the bottom, and off you go. Or there's variations of that. There's regional variants of it. Now, I've had students in the past who've had calculus that they've just remembered the quotient rule as g prime times f prime minus f times g prime over g squared. And that's fine. All right, let's take a look at the first one. F of x equals 2x minus 1, the quantity 2x minus 1 times the quantity x squared plus 1. And they're asking for f prime of x. Which, once again, f prime of x is just another way of asking for the what? The derivative. Now, there are a couple different ways you could tackle this. Method one is, it ain't so bad to FOIL this out. You could FOIL this out first and then hit it with the rules we just came from. You follow? So if you multiplied all this out, did your FOILing, then you'd hit it with the sum and difference rule, hit it with the constant multiple rule, hit it with the power rule, then you'd be done. And that's written out for you on the handout. Okay? But we want to use this to practice the product rule. So product rule says, I see I've got a product. Product, I've got to multiply. Right? So if you say the word times, if you've got an x thing times another x thing, that's your signal. We got to use product rule. Product rule says we take the derivative of the first factor times the second plus the first times derivative of the second. And now I look in and take the derivative of the first factor. So what's the derivative of 2x minus 1? Well, that's the derivative of 2x minus derivative of 1. What's the derivative of 2x? Let's go to the next slide. So far, so good. What can I do with this 2? Bring it out. What's the derivative of 1? 0. That's all times x squared plus 1. Plus 2x minus 1 times. What's the derivative of x squared? 2x to the first, or 2x, plus what's the derivative of 1? 0. And last but not least, what's the derivative of x? 1. And then if we clean up here using the algebra, let's see what we get. We got a 2x squared plus 2 plus a 4x squared minus 2x. So when the dust settles, how many x squared do we have when it's all said and done? Six. How many x's do we have? And then what's the constant? Okay. Make sense or not, folks? Now, if you've had calculus before, good. If you're taking your derivatives and you're comfortable with things, good. If you're first starting out, I recommend writing out every single little step, because that'll solidify the process for you. Because, spoiler alert, the last 3 weeks of this summer class, we're going to be reversing all these rules. Normally, that's just what happens. So I said the first half of calculus is differential calculus. The second half of calculus is called integral calculus, and we run all these rules backwards. So you really, and especially summer, you cannot get enough practice on these rules. All right, that's why the book homework is there and all that other stuff. You got to become fluent with derivatives, and you have 3.5 weeks to do it. Okay. All right. Number 2. Y equals 3x minus 1 over 2x plus 1. They're asking for dy dx. And once again, dy dx, that's just another way to ask for the what? Derivative. So once again, we think about putting an x in there. If you plugged an x in there, you'd multiply it by 3 and subtract 1 to get the numerator dialed in. You plug the x into the denominator, multiply it by 2, add 1 to get the denominator dialed in. And the last thing you would do to evaluate that expression would be the what? If you plug an x in, the last operation would be the division, which means the first rule we got to apply is the division rule. Now, can we make this easier on ourselves? Well, we're kind of stuck, because once again down there we've got addition in the denominator, which we can't really do anything about. So we're stuck using quotient rule. So once again, think of this as high over low, and here we go. Take low d high, so we take the quantity 2x plus 1 times the derivative of the quantity 3x minus 1 minus high d low, the quantity 3x minus 1 times the derivative of the quantity 2x plus 1. We square the bottom, and off we go. So that's the high function. Whoops. I circled the wrong thing with the wrong color here. So the high function is 3x minus 1, low d high, minus high d low. Low function, low d high, minus high d low. Square the bottom, and off you go. Does everyone see how we're plugging in the appropriate things to the appropriate places? All right. Now, let's think about 3x minus 1. That's a linear function, right? So the derivative is asking for the what? Geometrically, it's asking for the... Geometrically, derivatives are slopes. What's the slope of the line 3x minus 1? 3. What's the slope of the line 2x plus 1? 2. So we could go through the properties here, or we could say, well, I know we're asking for slope here, and I could just do it that way too. It's all good. It's all good. So I got the quantity 2x plus 1 times the slope of the line 3x minus 1, which is 3, minus 3x minus 1 times the slope of the line 2x plus 1, which is 2, all divided by the 2x plus 1 quantity squared. And once again, the rule of thumb in calculus is we simplify numerators and we don't multiply out denominators. And that's still true in derivatives. Now, some of you might be a little trigger happy here, and you might want to cancel out these 2x plus 1s. Is that a legal thing to do? No. In order to cancel from numerator and denominator, it has to be a common factor of both. In other words, you would have to factor this 2x minus 1 out of both of these things, which we don't have. You follow? So we can't cancel these. That's why we always simplify numerators and keep denominators as is. So let's go ahead and do that. 3 times 2 is? Now, common mistake is forgetting about that that's a subtraction, which means there's a negative that's going to get distributed to all these things. So I'm going to have 2 times 3x, which is how many x? But I've got that negative out front, so it's going to be what? Negative 6x. And then I've got the 2 times the negative 1, which would be a what? Negative 2, but I got a negative out front, so that's really going to be a what? Positive 2. So when the dust settles in the numerator, what do I get? There you go. So that's my final answer, dy dx. 5 over the quantity 2x plus 1 squared. Make sense or not, folks? So once again, on the test, there are 2 derivative problems like the ones we just did. You follow? It just says find the derivative, or, and then you do that, and you would be using these rules. The only time you want to bust out that limit definition on the test is when I specifically say use the limit definition, which I think on the test, there are no limit definitions. So when you're sitting there on the test, there are no limit definitions on the test. There's only that one on the take home. You follow? So on the test, when you go to take a derivative, use these rules. All right, find the equation of tangent line. So there's one like this on the test. Notice I don't say to use limit definition of anything, so we can use the rules. So go back, tangent line. Y equals f prime of a times x minus a plus f of a. So this is something, if you've done enough of these problems, you already know it, because that's your slope, that's the point on the graph. Or maybe you need to make a flashcard of it, whatever you need to do. You need to know how to get tangent lines. So in this particular case, the function they give you is x squared over 3x minus 1. And the x value they care about is x equals 1. So this is our a value. So what I need is I need f prime of 1 and I need f of 1. Now f of 1 I can get right away. F of 1 means to do what? Everywhere I see an x, I'm going to replace that x with a what? 1. All right, so what do I get out of that? 1/2. Okay, so that's all dialed in. But now I got to figure out f prime of 1. So I need to get the derivative and then plug 1 into it. And that'll give me the slope. So f prime of x is the derivative of x squared over 3x minus 1. If you imagine substituting in an x value, you would square it. Then you'd multiply it by 3 and subtract 1. And the last thing you would do is what? Divide. That means the first derivative rule you got to apply is the quotient rule. Low D high minus high D low, and you square the bottom, and off you go. Do we have a question? Or is that just someone popping in? Looks like someone's popping in. All right, so I got my 3x minus 1. Now, what's the derivative of x squared? That's 2x minus x squared. And what's the derivative of 3x minus 1? Well, think that's a linear function. Derivative's asking for the slope. What's the slope of the line 3x minus 1? 3. Now, can you cancel those 3x minus 1s? I know you're tempted to, but it's illegal, so don't. You simplify the numerators, keep the denominators factored. Is there anything you can factor out of the numerator? If you look at both of those terms in the numerator, is there something you can factor out? Yeah, you can factor out a what? There's an x you can factor out if you want. It's up to you. This would give us 6x squared minus 2x. Minus 3x squared. So when the dust settles, what's the numerator going to be? How many x squared you got? 3. Okay. So this would give me the slope at any x value. What x value in this problem do I care about? I want f prime at what? 1. So I plug that 1 in there. In the numerator, what do you get? One, denominator. 4. We all good getting to the f prime of x and the f prime of 1. All right, now we just plug in the plug it into the tangent line formula. So the tangent line, y equals f prime of 1 times x minus 1 plus f of 1. F prime of 1, we just worked out to be a quarter. And what did we get f of 1 to be? We got to go back a little bit. Half. And once again, we can simplify this. I got a quarter x. I'd have minus a quarter plus a half. That's going to give me what? Plus a quarter. Now, how do we check this graphically? So I fire up Desmos. What am I looking for? Put in the function, the original function, f of x. It's x squared, right? Over 3x minus 1. We're looking at the point 1 comma half. There it is. My computer's running dangerously slow, which has me worried. But. All right, let's fire up that tangent line. Y equals, what did we get? We got a quarter x plus a quarter. Boom. Near the point 1 comma a half, can you tell the difference between the graph and the line? Nope, that's your local linearity. We found the tangent line. Okay. This is a nice example because it really ties together all the stuff we've been doing in Chapter 3 so far. What a derivative is, what tangent lines are. All right, example 5, find all places where the graph of f of x equals 6x minus x cubed has a horizontal tangent line. Horizontal tangent line. So if I think about function doing stuff, if I have a horizontal tangent line, then that means the slope there is what? 0. So this is just another way of asking to solve where's the derivative equal to 0. You follow? And you're going to want to get used to this kind of algebra. Because this is going to be our bread and butter, not next week, but the week after. Okay? So the first thing we got to do is find the derivative. So we got to take the derivative of 6x minus x cubed. What's the derivative of 6x? 6 minus what's the derivative of x cubed? 3x squared. Good. There it is. Now I set this equal to 0. And we do a little algebra. So x is in only one term on the left-hand side, which means we can get all the x's by himself. So what would I do to both sides to get the term containing x squared by itself? Subtract 6 over. Then I could get x squared by itself by doing what? Divided by 2. Or excuse me, divided by negative 3. And then last but not least, how do I get x by itself? Extract square roots. Since I'm extracting an even root, I could either have a positive root 2 or a negative root 2. And once again, I can check these answers graphically as well. A couple different ways. Any questions on the calculus or the algebra here, folks? So let's fire up this function. 6x minus x cubed. And we're looking at root 2. So I'll put in square root of 2, comma f of square root of 2. And label that. It's up there. See how it levels out? So as I zoom in, what's happening? Oh, I lost it. There we go. See how it's getting flatter and flatter? You follow? You do the same thing with the other one. The other way to check this answer is, remember, if you've got the function typed in as a function of x, so if your variable isn't x, you want to change it to x. Because then you can graph this. So you can say, okay, well, what is the derivative? Take the function off. I'm looking for the derivative is 0. That means I'm looking for the what intercepts here. I'm looking for the x-intercepts, right? And 1.414 is roughly root 2. You with me or not? So you can do it that way too. So there's a couple different ways to check on Desmos. All right, let's look at example 6. So in example 6, they give us a formula for f of x, but they give us a graph for g of x. And then they ask us some questions. So I'm gonna get the handout here. So I know what the questions are asking. There we go, derivative rules. So they're asking for f of 0, f prime of 0, f of 3, and f prime of 3. All right. So let's write f of x down and get all these values. So f of x is 2x minus x squared. So f of 0 means everywhere I see an x, I'm going to plug in a what? What do I get out of that? 0. Now I need f prime of x. What's the derivative of 2x minus x squared? Well, what's the derivative of 2x? 2. Minus what's the derivative of x squared? 2x. So what's f prime of 0? 2. F of 3. Everywhere I see an x, got to plug in a 3. 2 times 3 is 6. 3 squared is 6 minus 9, negative 3. F prime of 3. 2 times 3 is 2 minus 6 is negative 4. So here's all my data for f and f prime at 0 and 3. Any questions on how we got that? Now they're asking for the same stuff, but for g of x. But they don't give us a formula for g of x. They just give us a what? A graph. So this is where we have to remember that the function values are the what values on the graph? The y values. The derivative values are the what values on the graph? Slopes. So let's look at the graph. G of 0 is the y value, which is what? 2. G prime of 0 would be the slope. So let's check this out. What's the slope of this line? I go over how far, and then down how far? I go over what? 1 unit, and then I go down how many? 2. So that means that the derivative at 0, the slope at 0 is what? Oops, negative 2. Everyone cool with that? Now let's go over to 3. What's g of 3? Looking at the y value there. The y value at g of 3 is what? 1. And now g prime of 3 means I'm looking for the what? Slope. So let's look at the slope over here. I go over 2, up 1. That's going to give you a slope of what? Positive 1/2. Does everyone see how we're getting the information for g? So now they want h of x. They define h of x as 5g of x minus f of x. And they're interested in h prime of x. So that's the derivative of 5g of x minus f of x. So we can apply the rules just like we did before. We don't know what f and g are, but it doesn't matter. If you were to plug a value into this expression, you'd figure out your g of x and multiply it by 5. You'd figure out your f of x, and the last thing you would do is what? Subtract. So the first derivative rule we apply is sum and difference. So this would be the derivative of 5g of x minus the derivative of f of x. Now that 5 is multiplying g of x, and that 5 is a what? Constant. So what can I do with that constant? Move it out front. So I have 5 times the derivative of g of x minus the derivative of f of x. And now I'll just use the more familiar notation. Derivative of g of x is what we call g prime of x. Derivative of f of x is what we're calling f of x. And this gives me a formula for h prime of x. Make sense or not, folks? So now I can just plug in any x I want. So if I want h prime at 0, that's going to be 5 times g prime at 0 minus f prime at 0. G prime of 0 I got from the graph. So I go back to that. G prime of 0 was negative 2. F prime of 0 was positive 2. So I get a negative 10 minus 2. That's a negative what? 12. Make sense or not, folks? And you do the same thing if you want h prime of 3. That would be 5g prime of 3 minus f prime of 3. You just plug those numbers in. And apparently, if you do that arithmetic, you get 13 halves. You see the process here, folks? You just apply the properties. Let's look at p of x. P of x is f of x times g of x. So clearly the p here stands for product, because it's the product of f of x and g of x, which means when we go to take the derivative of p of x, what rule do I have to use? You're multiplying f of x and g of x, so I got to use the what rule? Product rule. So I take the derivative of the first factor times the second, and then add the first times the derivative of the second. You follow or not, folks? And so if I want p prime of 0, all I got to do is plug 0 in to each of these things. F prime of 0 times g of 0 plus f at 0 g prime of 0. And now I go back to my table. What did we get for f prime at 0? What was f prime of 0? 2. What was g of 0? That was also 2. What was f of 0? 0. And what was g prime of 0? Negative 2. So when the dust settles, what do I get, folks? 4. Okay. And once again, if you wanted p prime at 3, guess what you could do? Just plug in the 3. Okay. The last one on there, q of x, is f of x minus 2 all divided by g of x. Q is probably standing for what? Q for quotient. Sure enough, if you plug an x into this expression, you plug it into f of x, subtract 2 to get the numerator dialed in. You plug it into the denominator, g of x, And then the last thing you would do is what with those numbers? Divide. So we got to hit this with quotient rule. So quotient rule says low D high minus high D low and square the bottom, and off you go. So this quotient rule works for any combinations you've got like this. Everyone good seeing where we're filling in the pieces here? So f of x minus 2 is high function. G of x is low function. You good with that? G of x times. What's the derivative of f of x? That's what we call what? F prime of x minus, what's the derivative of 2? 0. Minus f of x minus 2 times the derivative of g, all divided by g of x squared. Let's put in 0. Q prime of 0 would be g of 0, f prime of 0 minus f of 0 minus 2, g prime of 0, all divided by g of 0 squared. Now I go back, what did we get for g of 0? 2. What did we get for f prime of 0? 2. Minus, what did we get for f of 0? 0 minus 2. And what did we get for g prime of 0? Minus 2. All over, once again, g of 0, 2. Squared. So we got a lot of 2's here. We got to be careful. I got 2 times 2 is 4. I got 2 times negative 2, which is what? Positive 4, but remember it's being what? Subtracted. So sure enough, I get 0 over 4, which is 0. See how this is working or not, folks? Higher order derivatives. So what could be more fun than taking a derivative? Taking it again. For example, let's take a look at f of x. That's x squared. What's the derivative of x squared? 2x. Can you take the derivative again? Yeah. So how do we denote that? Well, one way to denote it is just use another prime. So f double prime means the derivative of the derivative, which in this case would be what? 2. Could you take the derivative again? Sure. Then you'd have f double prime prime or f triple prime, and that would be what? 0. Can you take the derivative of that? Yeah, it's going to be what? 0, 0, 0, 0, forever, right? Now, normally, if you get to more than 3 primes, it just starts looking ridiculous. You follow? Like if you wanted like the fifth derivative, 1, 2, 3, 4, 5 of x, that just gets weird. So often you'll see f parentheses 5. That'll mean the fifth derivative. that's one way that they can do higher order derivatives. Another way is you could use the fifth power on the operator here. This would also mean the fifth derivative. Or you could do d dx. Or d to the fifth y, dx to the fifth. You follow? So these are all the different ways they signify taking the derivative 5 times. Now, out in the wild, second derivatives are extremely important because of this law, F equals ma. Does anyone know what that law is? That's Newton's second law of motion. If you have a constant mass, then the force acting on that mass, which is causing motion, is equal to the mass times the acceleration. The acceleration is the derivative of velocity, which is in turn the derivative of position. So if you have your position function, the derivative of that, as we talked about yesterday, is velocity. The second derivative of position, which is the first derivative of velocity, that's acceleration. And so since the force is mass times acceleration, this is where we get second derivatives into the mix. Okay? And then there's third and fourth derivatives, but those typically don't. At least you're not going to see much of those in your freshman physics classes anyway. Okay? So there's that example. Let's go back to example 7 here. That's the same function we had yesterday. Or maybe not yesterday, maybe the day before. Find and interpret the acceleration function a of t. So let's look. S of t equals minus 5t squared plus 100t. They're asking for the acceleration, which is the second derivative. So the way you get to the second derivative is you first find the what? Derivative. So I got to find the derivative. Now since the variable here is t, I'm going to write d sub t, because I'm taking the derivative with respect to the variable t. Does that make sense or not? And now I go through and use the same rules we've been using for the last hour or so. What's the first rule I would apply to this expression? Sum and difference. So let's do that. What can I do with that negative 5? Bring it out front. What can I do with the 100? Bring it out front. What's the derivative of t squared? 2t. What's the derivative of t? So this s prime of t, aka the velocity, is minus 10t plus 100. Any questions on getting the first derivative here? Now to get to the second derivative, I just need to take the derivative of the first derivative. So s double prime of t, which would be v prime of t, that's the derivative of minus 10t plus 100. And once again, you could think of this as a linear function because it's t to the first power. I'm just asking for the slope of that linear function, which is what? Negative 10. So my acceleration a of t is negative 10. So we have a constant acceleration. The negative means the acceleration is pointing in what direction? Downward. What would the units be? So s of t is measured in feet, right? T is measured in seconds. So the first derivative, the velocity, that's a rate of change of position. So that'd be feet per what? Per second. Acceleration, that's the first derivative of velocity. So that's going to be what? Feet per second per what? Second. You follow? So the fact that the acceleration is negative means that the velocity is always decreasing. So if the velocity is, say, positive, and the rocket's traveling up, the acceleration is always negative, which means it's pulling the rocket what? Down. So if the velocity and acceleration are opposite, then is the rocket speeding up or slowing down? So velocity is going up, acceleration going down. What's going on with the rocket? Speeding up or slowing down? It's got to be slowing down. You follow? Because it's decelerated. The acceleration is negative. On the other hand, if the rocket's traveling downward and the acceleration is also going downward, then it's accelerating in the direction it's going. And so the rocket is doing what? Speeding up. Does that make sense? So if velocity and acceleration have the same sign, the rocket speeds up. If they're opposite, then the rocket does what? Does that make sense or not, folks? And so once again, thinking through these as rates of change. So we got that right there, too. Okay? And there's your homework.